Welcome to the Volume by Cross Sections podcast. I want to come back to this one figure from the last podcast. And if you heard me when I was typing the numbers into the calculator, I said 55, and I typed 55 instead of 57. So my warning is be careful when you're typing in numbers. I would have lost the point simply because I typed in the wrong number into the calculator. Just do a quick double check. Make sure you put the right numbers in because it was 69.125 degrees Fahrenheit, not whatever I said before. So just be careful when you put numbers in the calculator. That's all. And you don't want to lose points just for something silly like that. All right, so let me go up to volume. And we were talking about volume by cross section. This one that we're going to look at is a little bit tricky, but I think we can handle it. Right, so Cavalari's principle. So two solids with equal altitudes and identical parallel cross sections have the same volume. This allows us to calculate out the volume of figures that are not right figures. Right, we used this back in geometry with oblique figures that leaned a little bit. And so long as the area of the cross section is the same and the height is the same, the leaning doesn't matter. Right, it still will have the same volume. And that same principle is applied here when we're finding the volume of some unique shapes. Right, so we're going to be finding the volume of this wedge. We have a 45-degree wedge. It's cut from a cylinder of radius 3 as shown. We want to find the volume of a wedge. So some important things to remember. It's a 45-degree angle, which means that, let's see if we can show this height, this length here, is going to be the same, I can't really draw this in here very well, as the height. Maybe if I put it over, as the height going this way, right? So that's going to be the same, because essentially what we have here, although it doesn't really look like it, is a bunch of right isosceles. I think I'm going to lose part of my shape there. Oops, there we go. Right isosceles triangles there as we cut through the wedge. Okay, that'll come important when we're looking to figure out the lengths of things. We could slice this wedge several ways, but the simplest cross section is a rectangle. The top is flat, right? It's not rounded, right? So when we slice down, we will have a rectangle, right? So if we were to slice down, we'll have a bunch of rectangles. The radius here is 3, so it's important to note that this length here then is a radius, and this will be 3 as well. 3. All right, so now we've got to place this on a coordinate plane so that we can have something to integrate. Otherwise, we're not going to be able to find the volume of this. All right, so if we place this, so our cross sections are vertical, we're going to be integrating with respect to x. And so imagine here we have a rectangle. So this is our cross sections, they're rectangles. Right, and so here, well, pretend that's a rectangle. That's a pretty bad looking rectangle. I suppose I could do a little bit better rectangle. If I really want to do a good rectangle, I guess I could just use a shape tool here. There we go. There's our rectangle, right? And so it's over here as well. So I'll just kind of draw over here. So notice that the way I have the rectangle situated, the length there of that rectangle corresponds with the y value. Now I put this right at the center here, right at the origin. And this is symmetric, right? This is a semicircle. And we have a semicircle base here, meaning that all these rectangles are sitting on top of a semicircle. So this distance here is exactly the same as this distance here. So if one is y, because we're going vertical here, right? This is a vertical distance. Then if I go to the other side is y. So together this is 2y. Because I want to put the center of this right at the origin. So this is the origin right there. And why do I want to put at the origin there? Well, because it's easier. That's why I want to put it there at the origin. Because then I'm only dealing with radii. That's one part. Now we need the length of our rectangles. So, I mean the width of our rectangles. So what's the other dimension? Right? Well, remember this would be where this value here, where I'm trying to draw. All right, the height of those rectangles. Well, remember I said these are 45, 45, 90 triangles, right? So whatever, we're cutting at a 45-degree angle. So whatever the distance is from the edge of the wedge to wherever the slice is going to be the same as the distance from the bottom of the wedge to the top of the wedge. In other words, this is going to be an x. Now it's fine to leave the width of the rectangle as x, right? That's perfectly fine, but because it's just our x values. It's just as we're moving along the interval, it's our x values. But however, we can't just leave it in terms of y. It needs to be defined in terms of a function. Right now it's not. We're just saying it's whatever the heights are. Well, how are we going to know what the heights are? You can't just say, well, guess what the heights are. I need a way to figure out heights. And we're going to figure out heights with a function. So I need to replace that 2y with the function. Actually, I need to replace the y with a function. The 2 is perfectly fine. But the y needs to be replaced with a function. You can't just call it y. All right? So if we think about the shape of the bottom there is a semicircle. It used to be a whole circle, but we cut off half of it. All right, so formula for the equation of a circle is x squared plus y squared equals 9. And everything that's on here I'm kind of talking through. I'm not necessarily going in the order. Right, so our volume, right, is we just have to integrate area. Right, so if we integrate the area, we're going to have r and dx, as this will be with respect to x, because it's vertical cross sections. We're going to have our volume. So our area, this is a rectangle. The area is the length times the width. If we integrate area, we've got volume. Right, that's what volume is. Put a V here for volume. The x is fine for a width because those are our x values as we move across the interval. But the y values, the heights have to, for each of the x's, has to come from a function. So if we replace it with the formula for a circle, then we'll have our function. However, I don't have a whole circle. All I have is a half a circle. So semicircle is basically going to be, if we solve for y, this is going to, the square root of 9 minus x squared, that's a semicircle, right? I'm going halfway, right? I'm not going to have the negative values because I don't have the other half of the circle, which is perfect because I didn't want the other half of the circle to begin with. And B, I have to have equations in one variable to integrate. Otherwise, you are stuck, right? There's no implicit integration. At least I should say there's no implicit integration in this class, right? That's called multivariable calculus, and you will have to wait for that. But we can integrate in one variable. So let's rewrite that equation of a circle as the equation of half a circle or a semicircle. Right, so now we have a semicircle. So now all is good. So now we're going to replace the y, which was just some y value from some function, with the equation that could represent the y. Right? So I figure it out in terms of x's and y's, and then I sit back and I say, what function is going to represent my y? And the function that's going to represent my y here is going to be the function for the semicircle. So I'm going to replace the y there with the 9 minus x squared. This equation right here that I just underlined is exactly the same as the one above it, the 2y times the h times the dx, except our h is, and I tried to write that below, but it got a little crowded. Our h there is x. Our 2 stays. Our y is the function, square root of 9 minus x, and we're integrating with respect to x, so it's dx. This dx is also the heights of all I don't know how I want to say that. Part of me wants to call it width, and part of me wants to call it height. But as we're summing them up, right? So this represents the thickness. That's a better. I like that better. Doesn't get confused with base and height. The thickness of all of our slices, of each slice. So the thickness of the slices is dx. Right? It's a little change in x, given that change is getting infinitesimally small. So that means we're getting infinitesimally many slices. Right? And we have infinitesimally, that's a hard word to say. So as the number of slices increases infinity, meaning the width of our slices increases 0, we're integrating, we're finding the sum of the area under the curve. And when we integrate the area, we get our volume. Okay, so our volume equation that we're going to be integrating is 2 times the square root of 9 minus x squared dx, 2x times the square root of 9 minus x squared dx. All right, and that's from 0 to 3 because, quite honestly, once you leave 3, you have no more wedge. It's only a radius of 3. Right? So it has to be from 0 to 3. That's as big as it is. All right, so we need to do a u to u substitution here because I have something under a radical and it's not just a single value, so I can't do it. All right, so u is going to be the 9 minus x squared under the radical. That means du is going to be the derivative of that, which is negative 2x dx. We have everything but the negative sign. All right, so we can deal very easily with the negative sign. We're going to do a u to u substitution. Going to kind of follow along with the chicken scratch on the bottom there. I changed the limits of integration. So if x is 0, u is 9 minus 0 squared, or 9. And then if x is 3, u is 9 minus 3 squared, or 0. Now, it should go from I plugged in 0 and got 9. That means 9 is the lower. Yes, I know 9 is a larger number. However, we plugged in 0 and got 9. 9 goes on the bottom because 0 was on the bottom. We plugged in 0 and, we plugged in 3 and got 0. 0 goes on the top. However, we got a negative there. So we can deal with this real nicely by switching it, right? So my little note here says switch. So just switch the limits, right? And make that positive. Right? Because when you change the limits, you change the sign. Right? When you change, I should say, the order. When you switch the order, you change the sign. So if I make it 0 to 9, with 9 being the upper limit, now that's positive. So now all I have to integrate is u to the 1/2, and this is going to be positive, but we're going from 0 to 9. So you integrate that, that's 2/3 u to the 3/2 from 0 to 9. No reason to plug back in. It was easier to work with the u anyway. So now all we have to do is plug back in, and actually over here I show you the rewritten one. All I have to do now is plug in. So you have 2/3 times 9 to the 3/2 power. So the square root of 9 is 3. 3 cubed is 27. 27 times 2/3 is 18. And the other half would be 0 anyway. So if I plug in 0, I'm going to get 0. So 18, and I don't know what it's measured in, cubic units is the volume of that wedge. Right? And that's how we're going to use cross sections to find the volume of things, of static things that are already created. Right? We're going to do something different if we're evolving something to create our volume. All right, so this was our first one, and I think this is the hardest one in the whole lesson. I think. So let me know if you have questions. I'm going to move on to the next one. All right, so suppose I start with this curve. All right, the curve I'm starting with is the one in black. It's the y equals the square root of x. All right, I kind of colored over this to kind of give it a more three-dimensional look. My boss at the Acme Rocket Company, where you work with Wile E. Coyote, has assigned me to build a nose cone in this shape. So I put a piece of wood in the lathe and I turn it into shape to match the curve. Right? Notice that, by the way, how did I know it's 4 inches? It's really hard to see. However, it's marked on here 0 to 4. So the length here, the distance on the x here is 4 inches. And I don't know what the radius is because the radius changes, right? The radius at the start of the cone, of the nose cone, is a lot different than the radius at the end of the nose cone, right? But I can represent all of those radii as being a function of the square root of x, because that's how we get all these heights. So every one of these heights here that we could possibly have, right, is just based on our square root of x. My heights are crooked. Of course I pull out the wrong thing. These were kind of crooked anyway. All All right, so let's continue. All right, so how could we find the volume of the cone? One way would be to cut into a series of thin shapes, flat cylinders. So if I cut this rounded figure down, so I got this because we have y equals the square root of x, and we kind of swung it around, right? And we have this shape that we created in the lathe. And so if I cut straight through this rounded shape, I'm going to have a bunch of circles, right? Flat cylinders, because technically, so I call it a circle because I'm thinking of its area, but technically it's a teeny weeny cylinder, right? Because dx is the thickness. So over here, technically, these really weren't rectangle slices. These were rectangular prism slices, but they were very, very thin slices, right? So they had a teensy, tiny, thickness, and so do these. All right, so the dimension that matters for a circle is the radius. And the radius here can be defined in terms of the y values. Well, what are our y values? Well, they're all the values from the square root of x, right? What about the ones down here below the x-axis? Well, I don't need those values, right? Radius just goes from the middle to the edge, right? I don't want the diameter. I can't work with diameter. That doesn't work with a circle. I want radius, all right? So I don't really care what the diameter is. I just care what the radius is. So the radius is defined in terms of the square root of x. So all our radiuses are the heights that we get from our function, which is the square root of x. The thicknesses of all our slices are dx, right? They're super thin, right? The thinness is going to 0. So the values of the cross section vary, as I have over here, as I have written over there. They vary, but all can be represented in terms of a function, and that's key in these problems. So in the other problem, we represented it in terms of a semicircle. In this one, it's in terms of the square root of x. Right, so the volume of each of our cylinders, so this is just the formula for the area of a circle. That's all. Right, pi r squared is the area of the circle times the thickness, dx. Notice we've just replaced r is the value of the function. So for the square root of x, we're going to replace r with the square root of x. That's where this comes from. That's just r. Right, and we square the radius and multiply by pi. And our thickness is dx. So we're going to integrate that. So this one is a really nice, easy problem, I think. So we can integrate that. I don't know if I put it on the next page. Let me just double check. Yes, I did. So I think I was done with this page. So we're going from 0 to 4 because you can't see, but it's 4 inches long, right? It's kind of hard to see on this one, but it is marked at 4 inches. That's just the end of our bullnose cone. All right, so the volume of each flat cylinder disc is pi r squared times the thickness dx. We add up the volumes. We're adding up the volumes. When we say add up the volumes, we're adding up the volumes of these little teeny these circles that have these cylinders that have such a teeny weeny thickness. That's why I kind of think of them as circles rather than cylinders, because their thickness is so teeny. It's like almost like a quarter but flatter. Right? It's going to 0. That's how teeny tiny those thicknesses are. All right, so when we're adding up the volumes means to integrate area. Right? So, and then the dx makes it a volume. So we have the pi we could just pull out. I often do. I have it shown over there. Just pull the pi out. It's a constant. And then you have x dx from 0 to 4. Well, that's x squared divided by 2. So the pi is a constant, the 2 is a constant. We're just going to plug into the 0 and the 4 into the function. You plug in a 0, you're going to get 0. So we're just going to plug in the 4, 8 pi, because we'd have 16 times pi divided by 2, and that's going to give us 8 pi. And that's how easy this one. This one I think is a pretty straightforward problem. I like this problem. All right, let's move on to the next one. I don't remember how long this lesson is or how many pages I have left. The only really tricky thing about this one is you have to visualize it. I can't seem to draw it well. And so you're going to have to kind of visualize it. Think like a loaf of Italian bread. All right, where it has this rounded, it's flat on the bottom and it's rounded, right? So we're already given our function. So y equals the square root of x is our function. All right, and this one is being integrated from 0 to 9. The cross sections are semicircles with radii because we have a rounded effect here. So you see that square root of x, that's a rounded top, not a flat top. And so the red loops there are trying to show it, and I'm trying to draw it. But each of your cross sections is a semicircle, right? A half circle. And the radii there, actually it's better drawn on the other picture. That looks terrible. What I have drawn in is, I guess, as good as it gets. If I go all the way across to the bottom, I have a diameter. If I go down this cross section here, if I just go halfway, I have a radius. So you got to kind of imagine this. It's the shape is created by the square root of x, but it's a rounded top, and that's the best I could draw it. So you have to kind of imagine I'm taking this, and this is my bottom, if you will. Okay, so this is the bottom of my figure, and then it's got semicircles on top. So my typical cross section is a semicircle. So I hope that kind of makes sense. It's like I got an area and I plucked a bunch of semicircles on it. The cross sections are semicircles with radii r equals the square root of x divided by 2. If I go all the way to the bottom, I'm going to have the diameter, right? Because it's plucked on top. So do you see how the best one is the very first one on the edge there. So it's a semicircle on top of that shape. That's how I'm trying to describe it. And so halfway is going to give me my radius. It's a little bit different problem than the other one. The other one, you notice, went below the function, and so we kind of created this bullet shape. This one is different. It's a flat bottom with a rounded top. The width is dx. That's the width of all of our little of each little piece is a dx. So we have an area of a cross section is going to be 1/2 pi r squared. We just replace the radius with what it is. The radius is the square root of x divided by 2. It's halfway, because the whole thing is going to be a diameter. There's nothing below there, right? So the square root of x is the bottom, and the semicircle is on top of it. So it follows that the volume of the solid is given by, so now all we have to do is integrate. So now I just simplified it down here. So I replaced the square root of pi divided by 2 squared. I just simplified that out. So square root of x divided by 2 replaces r. If we square it, that becomes x over 4. Right? And then I can pull out the 4 because that's just a constant. We have x over 8 pi. So we're going to integrate pi over 8x, because I'm going to pull out the pi and I'm going to pull out the 8 and just keep the x, right? Because pi over 8 is a constant. So the volume here, and we're integrating from 0 to 9, is pi over 8 times x dx. So pull the pi over 8 out. The integral of x dx would be x squared divided by 2. So now that gives us, when we multiply that by pi over 8, we get pi over 16 times x squared. And we're integrating that from 0 to 9. And now if you just plug in the 9, if you plug in the 0, you're going to get 0. So we have pi over 16 times 9 squared. It gives us 81 pi 16ths. That's the width, that's the volume of the entire figure. Right? The best way to think of it is a loaf of bread, a loaf of Italian bread. And the bottom looks like the square root of x, right? And the top is a semicircle. That's the best way I can describe this one. So the hardest thing about this is just visualizing what this thing looks like. Let's move on. I think I can do one more problem. All right, so this one, our base is a triangle. I've got semicircle. So imagine that something that's got a bottom that's a triangle. So now you've taken your Italian bread now has a bottom that looks like a triangle. Maybe you weren't very good at rolling it out. So one end was really, really skinny. And the top of it are these rounded semicircles. So we want to find the volume of the figure formed by x equals 0, y equals 0, and y equals 1/2 x plus 2. So those three lines, right, create our shape. We have a triangle shape there, but that's not what's important. The important is the cross sections, right? The triangle shape is going to help us define that. That defines y, and that defines what the values are for the cross sections. It defines what our radius is. But the shape is not the triangle. It's the semicircles, because it's got cross sections that are a semicircle. So if I slice down into this thing, it's a bunch of semicircles. It's got a rounded top. It's three-dimensional. So r is going to be half the distance from y equals 0 to the line there, right? Because if I go all the way, I've got a diameter. So my r is just 1/2 negative 1/2 x plus 2. Right? And then I have to find my limits. My limits are where the lines intersect. Right? So they intersect. If I set 0 equal to 1/2 x plus 2, right, that's going to give me my x-intercept. So for x equals 0 is one value, that's our starting value, and x equals 4. Because we're integrating with respect to x, it's those x values from 0 to 4, that's giving us our interval. And then the y values are defined in terms of half the distance from the line y equals negative 1/2 x plus 2 to the x-axis. So the area of area of a circle is pi r squared. So just replace the r with 1/2 x plus 2 and square. Right? So if I'm kind of looking at my number. Oh, the whole thing is squared. Excuse me. So I have 1/2. The radius is 1/2 times negative 1/2 x plus 2. That's the whole radius. Right? So I'm squaring 1/2 times negative 1/2 x plus 2. I distributed the 1/2, so we have negative 1/4 x plus 1 squared. So the 1/2 is being squared, right, because it's part of the radius. Right? It's this whole thing, negative 1/2 x plus 2. It's 1/2 negative 1/2 x plus 2, because it's half the distance. Right? So we have then, we square that, that would be 1/16 x squared minus 1/2 x plus 1. Right? So we're going to integrate that. We can just pull out the pi over 2 because that's constant. We're integrating from 0 to 2. I don't know whether I put the rest of this on the next page, but when you integrate area, you get the volume. And let me see what's on the next page. Otherwise, I could plug it in, but I don't really think I did put it on this page. I don't really think the integrating and the evaluating are much of an issue for anyone. I think it's just how to set these up. Right, so we have pi divided by 2, and then we integrate 1/16 x squared. That's going to become 148 x cubed, and then minus, that's going to become negative 1/4 x squared, because we increase by 1, and then plus x. All right, so now I just plug in the minus 0, since they all have x's, it would just be minus 0. It's a good idea just to put the minus 0 in there to show that when you plug it in, like you're supposed to plug in the upper minus the lower, but the lower is just going to give you 0. All right, so you're showing that you're supposed to plug it in, and that value you happen to get is 0. So we have 1/48 times 4 cubed is going to give us 4/3. 1/4 times 4 squared is going to give us minus 4, and then plus 4. So that's going to be, when we multiply that by the pi halves, we're going to get 2/3 pi. That's the volume of the whole thing, 2/3 pi. Not a whole lot of volume right there, is it? All right, so remember, with these cross sections, it's the shape of the cross section that defines which formula you use in terms of area. The function itself gives you what you're going to plug in for the variables, right? That's going to give you the values for your y's. And I'm going to end this right here with this one. And another lovely, the worst thing on these is me trying to draw the cross sections, make something two-dimensional, three-dimensional. But I'm going to end it right here, and I'm going to begin with this podcast, with this problem next.